Welcome everyone to the School of Computational Science and Engineering Convocation and the special lecture that we have arranged for today. To introduce our speaker, we have our Dean of the College of Computing, Zvi Galil.
I would like to start with an apology. I had to run away also in the panel discussion, and I may not survive the David's talk simply because what happened is I first went to Boston a couple of days last week, and the week before it was single digit, but everything was fine. And then I was in Rio 3 days last. I came back yesterday. It was 95 degrees, 110 in the sun. Everything was fine. And then Dawn, my assistant, sent me email, "Don't come back. Everybody here is sick." And I should have listened to her. So in order not to disrupt the lecture by my sneezing and coughing, I may have to beat a retreat like I did in the panel discussion. So it's really a pleasure to introduce David. I was Dean at Columbia, those of you who don't know, for 12 years, Dean of Engineering, and I had a couple of achievements. And one of the two was to attract David to Columbia. And he came even though he got a very, very funny name, a name of the chair, so he, nevertheless, he came. But that's, he came to a school. Columbia is not a college, it's a school that's also called after Fu, but you know, if somebody gives us $26 million to the College of Computing, I'll take any name. So it's really a pleasure to introduce David. Somebody asked me, hey, tell some joke about David, or make fun of him, or embarrass him, but it's actually impossible. He's a great guy, a great scientist. We were really very, very pleased when he joined us at Columbia. Maybe the only thing that might seem negative about him, which is really positive, is that he's usually in two places and sometimes three at the same time. So he used to be in Old Dominion, but also Lawrence Livermore. Columbia and Lawrence Livermore. And now he's also, as he speaks here, he's also in Saudi Arabia. So now, there are people, you know, my approach to this kind of people that spend time in several places, there are some people in one place and are not very helpful. Cause lots of trouble. You would prefer they would be in 0 places. There are some people in 2 or 3 places that are asset to each place they are. And David is such a guy. So actually, when he was traveling, he was not there. He's wonderful in all 3 places. So Columbia really was fortunate to get him, and my only criticism on him now is that he's in the wrong place.
No, I'm in the right place. I'm at Georgia Tech.
And you know, and actually he's the right speaker for today because I quote to you something from his website. Author or co-author of over 100 publications in computational science and engineering. So I guess he's the right speaker. So, without further ado, it's really a pleasure to have David with us and listen to him about, you know, what it means. I learned something about it.
Thank you so much. Thank you. Thank you. This is such a pleasure to be sharing this opening with you. I love beginnings, but I especially love enlightened beginnings and about, of course, computational science and engineering. And I feel as though we've already celebrated because we've just heard several wonderful prospective talks at the panel discussion, mini talks that in fact lay out the scientific promises of, I would say, not just the third paradigm, as your Vice President for Research said, but also the fourth paradigm, which is data-intensive computing, where you don't yet have the model. And the world benefits every time a university takes a strong organizational stand to recognize computational science and engineering as a discipline, if you will, or an interdiscipline that needs this kind of security and promotion, so it's not dependent on just a center. I would like to say, I know very well from their graduate student days the three most recent and therefore, according to Richard, most intelligent members of your faculty. I certainly knew Edmund when he was a grad student, and Rich when he was a grad student, and George Biros. In fact, I tried to recruit both George and Edmund to Columbia, but of course they got away and came to a place that gives them a better and more secure place to develop their art. And of course, I've known your influential departmental builders, David and Haesun, for a long time. Haesun was once, for a brief time, my NSF monitor. And Richard and I have showed up at a lot of workshops to promote CS&E as a discipline. And of course, my favorite dean of all time in many universities, Zvi. He's very supportive and very eloquent and really makes engineering sound like the best subject at a school. So I know he's going to do that at Georgia Tech with respect to the School of Computing. The whole upper administration will be singing this school's praises because he'll represent it in such an articulate and powerful way. So let me begin actually by pointing out to you that you've launched your school on a very auspicious day. This is actually the birthday of Richard Hamming. He was born on 11 February 1915 in Chicago. You can see some of his interesting quotes here. This is probably his most famous quote: "The purpose of computing is insight, not numbers." Yeah. There are a lot of good quotes. I like this one too. If you don't work on important problems, it's not likely that you'll do important work. Of course, he was the third Turing Award winner ever. This is the Nobel Prize in Computer Science, as people know, and of course, member of the NAE. And for those of you who are young scientists, or even not so young, I could commend to you his famous lecture, "You and Your Research," which you can find many places reproduced on the web, which has practical tips for career success for a researcher, including such things as who do you eat lunch with? I mean, really practical things. And of course, it's a rich source of quotes from the beginning and the sort of glory days of Bell Labs, when everything that you and I use, like C and Linux and all those things, were actually being invented down the hallway. And there are a few semi-annoying anecdotes of life at Bell Labs from the same era to do. And then just before, the year before he died, he wrote a book called Learning to Learn. So anyway, a very interesting figure, perhaps the last figure in information technology to combine both the discrete and the continuous before each one became too specialized to keep up. His own doctoral dissertation was in the numerical solution of ODEs. Of course, his real fame came from error-correcting codes, and his work is in the heart of just about every computer today. But he really did bridge those two worlds, and therefore he makes a very strong candidate for an inspiring figure on your birthday, same as his birthday, in terms of managing to keep those two worlds together and integrated, because as my talk will indicate, we need a lot of combinatorial and discrete stuff to help at the exascale, which fundamentally is a floating point type of high resolution world, and we probably even need machine learning on the machine. These machines are really hard, they fail a lot. And so it's really sort of a good integration for a division like this, now a school like this, to keep those things together and to keep Richard Hamming as a good model. Supercomputing has become a scientific instrument, and in this way Richard Hamming left himself vulnerable to being overturned by history. Remember, he said the purpose of computing is insight, not numbers. But of course, the purpose of computing today is actually numbers. I mean, you heard Professor Sherrill say that. We want to get down to 1 kilocalorie per mole or less for a bond or the energy of a molecule. Richard Langer, a physicist selling the US SIDAC program in Congress in 1999, SIDAC came into existence in 2001 and has transformed computational X, where X is, any number of things, astrophysics, biology, and so forth. The computer is literally providing a new window through which we can observe the natural world in exquisite detail. If you were the president of a university and you had $100 million to invest, you could choose any number of facilities that served a single discipline. But if you bought a supercomputer, and equally importantly, if you collected a small staff around it to enable people to port their codes to these hostile, distributed, hierarchical memory environments, you would be serving all of the disciplines. And I challenge you to make that your role in some unofficial consultant way with all of the excellent departments around you, including, of course, engineering at this top 5 engineering school. I have to give some credits to this talk. I'll say a lot of things not on my own authority, but on the authority of some of the best minds in the DOE and the comparable agencies around the worlds of Asia and Europe. Just this month was published, finally, a fairly, let's say, converged version. Of course, things will evolve rapidly, but the community is happy with this lengthy roadmap that's appearing in the International Journal of High Performance Computer Applications. Two people in the room, I think, are part of this, myself and Jeff, but it's quite an international audience, and you can see the multiple sponsors. And a lot of what I say, again, comes out of what I consider pieces of this report that are relevant to my own area, which is algorithms for these hostile architectures. I wonder, should we bring down the lights in front, or can people see the dark slides well enough? Would that be? Okay. So this is a famous extrapolation on a linear time log performance scale, showing why the idea of exaflops, that upper rightmost triangle, is not outrageous. This is the top machine on the top 500, and the 500th machine, a little bit more stable. And it only takes 8 years to fall from #1 in the world to fall off this list, because every decade we go, 1,000 in power, and the difference between any of the top and the bottom machines is about a factor of 100. 100's a good economic sweet spot, to be down around the 100th or the 500th machine. To be the pioneer machine is expensive and a little bit risky in terms of the port usually. But the Exascale by 2020 appears to be, a given win. Of course, what I will argue is that it's actually a qualitatively much different thing to get there than the last several orders of magnitude, from giga to tera to peta, and so forth. The international community, recognizing the daunting nature of literally hundreds of millions of euros or dollars of software that needs to be redone, has started just at the very beginning to work together through this particular initiative. It's G8 minus Italy, I guess, and the world is collaborating on coordinating where the investments have to be made in porting the world's software to this upcoming environment. So I'd like to consider with you today why push to the exascale. That's a short and easy section. You just heard a few talks on it, and I won't try to spend too much time. I'll look at it from the point of view of an oil country, maybe. What will systems 1,000 times faster than today's look like architecturally? That's actually not such a hard question to answer, because it's pretty close in time, and we already see the genes of these machines forming. But the third one will lay out some really harsh boundary conditions for moving codes onto these architectures. And then the real heart of the talk is, how are we going to prepare for this algorithmically now? Well, the easy question is, why push to extreme scale? I don't know how many of you applied for the Department of Energy Computational Science Graduate Fellowship. By the way, a very good program. I don't know that we have people here. But if you do the third essay in that application, which you can go to on the web today, you will get these questions. Why go to the petascale? And here are 8 or 9 reasons. Better resolve a model's full natural range of length and time scales. You just heard what those are for molecular dynamics in biology. Accommodate physical effects with greater fidelity. Put in the real model that you know, not some hybridized or homogenized model that you can afford. Allow the model degrees of freedom in all of the relevant dimensions. Could be 3 plus time, could be 7 if it's a phase space calculation with Boltzmann. Better isolate artificial boundary conditions, or better approach realistic levels of dilution. You heard about that in terms of the solvent problem. If you don't have enough power, you can't make things physically, realistically dilute. There's not enough background to hide them. We want to always combine multiple complex models. Once we have an atmospheric model and an ocean model, we want to build a climate model. We want usually not to do a forward model and gasp and die at the finish line. We want to use a forward model and combine it with data from the real world to improve both the understanding of the data and the model. Two ugly parents, simulation and data, somehow have a beautiful child if we can use them in a data assimilation. That requires storing the data, running the massive simulation, and running it many times so that they inform each other and correct each other. We want to perform optimization, as in engineering design, or control of complex systems that we human engineer. We want to quantify uncertainty. One of the reasons the government will pay for an exascale machine, maybe, is because it will support policy, like carbon budgets or weapons security. And in order to do that, we really have to be more reproducible and really have error bars on simulations, something that we haven't ever really worked on as a discipline. And of course, improving statistical estimates. Monte Carlo is a 1 over square root of n kind of convergence rate, very slow, and we need sometimes to run lots of things. And I would say these are all third paradigm reasons. These are all simulation-based. These presume you actually have a model, Schrodinger, Maxwell, Navier-Stokes, et cetera. There are many areas where we don't yet have models in biology and nano and so forth, and there we have to depend simply on learning things from lots and lots of data, medicine, social things, economics. These are areas where the supercomputer, the exascale computer, really you should think of it as an exabyte computer rather than exaflop computer, but you need the flops to make good use of, if you're going to power up all those bytes, then you need the parallelism to explore them. And unlike a lot of scientific codes, which are sort of information theoretic optimal, I mean, we can solve a Poisson equation in log-lin time relative to the number of observations in the field, but a lot of these machine learning algorithms are highly superlinear, so that they actually choke on big data sets, and we certainly need exascale systems for them. Well, the third paradigm was championed, ironically, by a mathematician in a physics journal and by a physicist in a computer science journal during the 80s. We got from Lax the idea of the third leg of the stool, and from Wilson, the Nobelist, the Abelist, and the Nobelist, the idea of a grand challenge problem that could not be addressed by experimental means alone, certainly beyond the theoretical accessibility. The fourth paradigm really, in most people's minds and ways of talking, came about in this landmark paper in 2006, where Jim Gray, having realized that data was doubling about every year, said, it's not enough to have data, you have to organize it, you have to have ways of retrieving it efficiently, and you have to have machines to go over it, because humans are not doubling a year, and they're not all trained to look at data. And we can't save all that data, so we have to do a lot of it on the fly. And there's, of course, this new book, The Fourth Paradigm. You can download it free from Microsoft, where Gordon Bell has written the foreword, as you can see there. And this one, to me, is a little bit disappointing from the point of view of this school, because this is largely about machine learning and data mining in medicine and economics and social stuff. The same kind of things can be done in the sciences, but I don't think we're quite up to our cousins in having true discoveries that were made by data mining only. But I think we'll get there, and maybe that will be several of your theses. I wanted to highlight that word inverse problems just to graphically illustrate what I mean by that. When we have a differential equation type model, we've written down the physics, F equals ma, or conservation of mass, momentum, energy, whatever it is. We have boundary conditions forcing some parameters that may or may not be known, the viscosity, the permeability, and so forth, some initial conditions. And we know that we have a well-posed problem. If we put all those things in and we believe them, we can get usually a unique solution that depends continuously on those inputs. But the inputs may be very uncertain. For instance, permeability in an oil field where we don't have a map of the underground. But we do have decades worth of history of oil being pumped out of that ground, and we have drilling here and there, and we have seismic. So we have a certain amount of information about the solutions of these problems, which enable us, in combination with samples of the coefficients, to get better estimates of the parameters. Unlike the left-hand side, this is not usually a well-posed problem, but we can bring various ideas that we have from the physics of the situation in to regularize the problem. And this is really an ambition of large-scale computational science, to go beyond the one-off, if I put these things in, what do I get out, to I want to get out certain things, and how can I use the information I already have in the solution form to back that out. So I listed 8 or 9 reasons to go to extreme scale. What would they look like, for instance, for an oil company like Aramco, the world's biggest company, where which looms large in Saudi Arabia at the moment? Of course, the first one is pretty trivial. You have some reservoir. It takes 5 hours to drive from one end to the other of the Gavar Reservoir. We need an exascale system to put a mesh point every 25 meters and the requisite depth. The physical effects, we don't want to just do black oil. We want to fractionate it into different carbon lengths and different phases and different amounts of water and polymer that we might inject to get tertiary recovery. We certainly need 3 dimensions and time. You know, an axisymmetric reservoir just doesn't tell you much, other than maybe a little bit of intuition in the Hamming sense. But we, of course, don't know, you know, the whole underground of the Earth. If we want to solve something for a certain period of time, we should make the boundaries at least big enough to contain the fastest transit, you know, during that time. And everything beyond that, we need, you know, we need to buffer ourselves from a little bit of uncertainty. We, of course, want to use historical production records to learn what's left. And so, you know, right now, typically 30% of a reservoir is recovered. That's actually good news. That means 70% of the oil is still there for some future smart generation to find after the, you know, so-called proven reserves have come out. But it takes a lot more energy to get it out. You don't just poke a hole in it and it comes. We want to do multiple complex models. When you produce a reservoir, you change the seismic properties. You may change some geologic properties. And if you can combine all these models, you really can do much better. You want to get the right strategy at the beginning so that you leave less oil behind. You can only do the experiment once. So you want to do the simulation hundreds of times before you start wasting the one-of-a-kind reservoir. You want to you know, bound the error in the outputs in terms of the errors in the inputs. You want to you know, improve statistical estimates by, you know, testing certain inputs as random. And this is a picture from Aramco used by permission showing their previous capability, their mega cell simulator, and a gigacell simulator which can afford much more spatial resolution, up to say an order of magnitude in each dimension. And you see here 2 pockets of oil that were left behind, or invisible, if you will, under the coarser resolution of the same scenario run at 2 resolutions. But I would argue that the need for extreme scale goes beyond this simple example of one reservoir. Oil companies are vast. They have dozens of reservoirs, many refineries, many transportation systems. Think not of the science or engineering problem of pumping, but think of the economic problem of maximizing profits with a system like this. Think of the constraints of supplying the own country's needs and figuring out what grades to refine for different types of exports, because a single gallon of crude can be made into many different kinds of things, and they have different prices at different times, and they take different amounts of energy and resources. You have tens of thousands of valves, not just the physical valves, but, you know, the people, and do you want to put a reservoir here, a refinery there, etc. And this is a huge, massive, nonlinear, and most likely non-robust, meaning very sensitive to changes of inputs, constrained optimization problem. I mean, you can't describe, you know, how complicated this thing would be to solve from first principles. They're certainly too complex for a self-contained, self-consistent theory. They're unsuitable for experiment because you can only do the experiment once. Engineering heuristics are useful and used, but the career, you know, engineer attached to one refinery is a thing of the past. You know, humans move around a lot nowadays. Things in the world economy change much more rapidly. So simulation, the third paradigm, is very useful for at least exploring scenarios before executing them. And probably data mining and machine learning are even going to be more important because of the ill-posedness of this optimization problem. Well, that was one field. You heard about chemistry and biology. Here's a bunch of fields for which experts got together at the last Exascale meeting. Maybe you can find your favorite one there, or maybe you should have been there to make sure your favorite one is there. 7 of the applications represented at this workshop that I just showed you the topics of were already Gordon Bell Prize winners. These were people like your George Biros that have already run at the edge of today's machines. So they're relatively informed customers for the next machine. By the way, I think Edmund Chow is also a Bell winner. So you guys are rich in this department. So these are not necessarily representative of all the problems or even the most important problems from the contributing countries, but they were a collection of PIs who came to my breakout session. And I asked them before we started the breakout, characterize your problem in terms of what programming models you're using, what is your current scaling performance, what algorithm dependencies do you have, what libraries do you use, and how do you balance the machine's resources in your computation? You know, I/O versus computing, communication versus computing, synchronization, versus computing. And how do you scale? Can you scale strongly if that's relevant, like for something real time? How can you scale weakly? What is the ratio of memory and flops, or the power between memory and flops that you need in your scaling? And so I'm sure you're curious about the answers, and there they are. And I'm sure you can't read them. So I've made a few digests for you. And actually, this was surprising. Well, the first part is not surprising. I thought everything was bulk synchronous, MPI, single program, multiple data, whether it's domain or particle or other kind of object decomposed. But actually, it turns out that the chemists, for some historical reason, have always used globally shared memory rather than distributed memory. And they have a large number of very well-developed public tools like MPI for breaking down their problem and queuing it and load balancing and so forth. Many codes have multiple phases that do not have compatible load balance decomposition. Think of like a celestial mechanics computation. The masses of the stars tend to be concentrated in certain low-dimensional regions, whereas the mesh, is probably fairly uniform. You may not have the real estate for the universe load balanced the same way the point particles for the push phase are balanced in the universe. So you may either be exchanging data at long ranges so that it's co-located correctly, or you may have to rebalance between every phase. And either one is a real drain on the scaling of the simulation. Many are already running in hybrid mode. We're already living in the post-MPI world, usually today with OpenMP, but CUDA, OpenCL, and so forth. And typically, the things that show up at these meetings are already weak scaling to their heart's content. And the bad news is weak scaling ends, because we can't afford any more memory to go with the flops that are coming. Flops are cheap, memory is expensive, and that's one of the reasons we're turning a big corner from PETA to Exa. Just a few other things to characterize the field. The majority of the apps are already bandwidth limited in most phases. If you threw more processors at them, they couldn't use them. They can't move the data out of memory to more processors in time. The flops provided storage is generally already optimal, linear or log linear in weak scaling. I/O versus computation, the people that showed up weren't so concerned with I/O. I mean, I/O is important if you're modeling turbulence and you need to dump a movie frame every second. But if you're doing quantum chromodynamics, you put a field in and 2 weeks later you get a scalar out, right? The mass of the proton or something. This is not an I/O killer. But no matter whether your run produces a lot of I/O or not, you can expect checkpointing to be much more important at these non-resilient exascale machines. In terms of communication versus computation, those who are successful in weak scaling have learned how to defeat Amdahl's law. They have a replicated chunk of space, or chunk of atoms, or chunk of agents, and it's got a fixed, computation bulk to communication surface kind of ratio that fits well with a given, granularity of the computer. And you can replicate that. You add more nodes, you add more of these chunks, and you can weak scale. And that's a pretty successful thing, and it doesn't really show a sign of ending, except for running out of memory to weak scale on. Synchronization is really important. We are addicted to synchronizing algorithms in computational mechanics and chemistry and biology, because we live in a causal world, and we tend to be explicitly time-stepping or solving an equilibrium problem, and we can't let different cycles of the computation get out of phase with each other. And this is going to be a real limit on an exascale system, unfortunately. The core algorithms are really, I'd say, no surprise. Your successful hierarchical algorithms like multigrid for equilibrium PDEs, fast Fourier transforms, fast multipole methods, maybe some n-body, maybe some AMR, and so forth. The minimal library dependencies, bear in mind this is an international conference, but I think every one of these packages, except maybe for MUMPS, is written in the US DOE. I mean, we give away our software. We get something back for it. We get it debugged on the field, and we get contributions to it. It's an open source world, and people have learned to use these things. I mean, there's a variety of things. The top ones are mostly numerical things. Here's a graph lib. Here's some object-oriented stuff. Here's a mesh discretizer, visualizers, and so forth. I/O systems in here. And so that's the end of this primary source data that I collected. And now I will sort of try to make something of this train wreck that's coming with Exascale. David already talked a little bit about it from the chemistry point of view in the last hour. So we can very briefly tell the optimistic side of the story, that the Gordon Bell follows the top 500 so far. Gordon Bell is real science. Top 500 is fake, benchmarks. But it's scaling well. We can even peek at the core of a motivating application to see where it's vulnerable, and then take a look at what's coming in terms of programming models and pressures on algorithms. You can look at the Exascale from 3 viewpoints, depending on your primary home in the university. If you're an applications person, you want to ask, what formulations? Do I use PDEs? Do I use integral equations? Do I use Lattice-Boltzmann? I mean, there are many ways of formulating a problem. Which one will live best on these machines? If you're an architect, you want to know, what are the various hurdles where the rubber hits the road that determine the cost and the power of the machine. How can we make it useful? And if you're an algorithms guy like me, you want to figure out how to bridge these two fixed aspects, and whether we have to give up time-honored things like separation of concerns in order to graft the application much more tightly to a given architecture and give up portability, as we may have to do. The philosophy of an algorithmicist like me is that you guys give me the applications and the architectures, and I have to make them work together somehow. And as the transformation of Moore's law from concurrency, from time speed-up based to concurrency based occurs, scalability remains as important as ever, but there are new memory bandwidth stresses that arise when you share these memories, and therefore the narrow straws to the memory. And the greatest challenge is maybe going to be the lack of performance robustness. When we assign a certain number of flops to a processor today, and we've gotten used to how its caches and stuff behave, we can pretty much assume that that same assignment on a million different processors will end at the same time. Because processors are very reliable, and we run them very uniformly. But at the exascale, this ends. Processors will power cycle. The difference between a 0 and a 1 in voltage will be so small that a high percentage of floating point operations will fail and will need to be redone. And we cannot count on regular lockstep synchronization methods to work in this power-starved environment. So knowledge of algorithmic capabilities can influence how we choose the other two things. But I would say, from an algorithmic point of view, knowledge of the application architectural opportunities can usefully influence algorithmic development. David, we just solved all your problems, but thank you so much for making it to this part. I know you had other commitments. This is a history of the Gordon Bell Prize up until last year. Of course, last year was Georgia Tech's fun year. I mean, one of them, I guess, with George coming in down here. You can see many different types of problems: PDEs, n-body, Monte Carlo, integral equations, density functional, molecular dynamics, and so forth. Applications from all over, mainly the sciences, as opposed to, say, aerodynamics or circuits or something. Mainly fundamental things that really challenge us to get to the edge of scale in nature. You can see the growing granularity increase in the computations, the collection of machines that have won, sometimes very special purpose machines like the gravity pipeline or the numerical wind tunnel here. And of course, ultimately, the performance rating, which is very non-uniform, because in one year or another, people submit problems of different difficulties. But the general gist is, every 10 years you get a factor of 1,000 in real apps, just like every 10 years you get a factor of 1,000 on the top 500 benchmark. For many years, you were getting a factor of 1,000 every decade in costs, too. These were giddy years when between 1989 and 2001, you went from $2,500 per delivered flop to 25 cents. And with the advent of GPUs, we ended a long drought where we didn't really do any better than this, because even if the processors are free, everything else costs so much. But after a while, the repackaging of things with GPUs for certain narrow kinds of computations have produced almost the same benefit. So you have 2 factors of 1,000,000, and so you have, a factor of 1,000,000,000,000 in price performance in some sense, if you could get these together. This has inspired a whole raft of government studies. I'm just showing you ones that I've been associated with in some way or other as a contributor or a co-editor or something. This is NSF, some DOE, and I think even one NASA one in here somewhere. Yeah, that one. And so many people have been inspired by these very giddy curves. You know, where else, in what other industry do you get, you know, a factor of 1,000 in 10 years? I mean, does college tuition go down by a factor of 1,000 every 10 years? I mean, you know, let's talk about price performance. So because of the optimism with which we can approach these multi-scale problems, you know, the agenda for a school like yours is quite clear, writ large in federal reports. By the way, I don't know if you can see this. See this report here, this fusion simulation program? It's my best cited paper. This is a picture, a scene from the movie Wall Street, Money Never Sleeps. This is Jake Moore, and he's trying to convince his girlfriend's father, who is a billionaire investor, to invest in the fusion simulation project. And here's a well-thumbed copy of my report. So, you know, I could say 20 million people have read this report. And there is Jake. One of his quotes in the movie is, you know, keep building that baby star, Doc. You know, he wants to actually commercialize fusion reactors. You should definitely go see the movie and look for the report. But you can download the report for free. So how are problems like these PDE-based problems, solved at the petascale today? Almost uniform paradigm is domain decomposition, whether it's cluster of particles, cluster of mesh cells, you know, chunks of surface area on a boundary integral simulation. What we do is we divide up the problem and we send a uniform type of task to a large you know, working force of nodes. And those nodes exchange information periodically at their boundaries because they're not truly independent. They can just do a certain amount of work independently between neighbor sharing or global synchronizations. So we have our single program multiple data paradigm, also called bulk synchronous, also called communicating sequential processes. Nearly all of the weak scaling things that we do today are built like this. So here's an example of a partial differential equation on a funny domain where you can see that, you know, if you apply some finite difference method or whatever, most of the degrees of freedom that interact are local to subdomain 2, but, you know, the ones at the edge, a lower dimensional set of the total, have to have some data exchange, which is reflected in the off-diagonal blocks of the matrix. And whether you're talking finite differences, finite elements, control volumes, you lead to some sparse matrix vector product that needs to be done, which Rich Vuduk has dedicated his career to making really wicked fast on a variety of very funny-looking memory hierarchies by all kinds of clever scheduling and blocking. You never want to invert these things. If you invert them, the storage explodes. But if you multiply by them, you know, you can contain the memory. And the question is, how many times do you have to use the forward operator in order to make up for one application of the inverse? And the good news is you can make it optimal. And there's a family of methods for nonlinear implicit solution of, you know, backward difference time-varying problems or equilibrium problems called Newton-Krylov-Schwarz, where, you know, basically Newton does a local linearization and solves a sparse matrix. Krylov actually solves that sparse matrix by building up a test space with matrix vector multiplies and finding the best fit in a small number of test directions. And it's kept small by these guys. And these guys take any good solver for the original problem and they apply them on all the subproblems. And so they're not solving it perfectly, but they're doing enough of the work to keep this guy's work down. Of course, these people never worked together, but they're very synergistic in post-mortem phase. Here is a graph of time versus time of different steps in that Krylov-Schwarz, that inner linear solver. So you have, like, say, n processes. Each one does a little local communication to scatter their boundary nodes to their neighbors. That gives them enough data to do their local block row of the matrix. Then they can do their preconditioner sweeps concurrently and without any communication. Then they do some kind of an inner product to, you know, basically make the test direction orthogonal or conjugate to the previous ones. And after they've done that, each one of them can update their local piece of the answer. And this is a loop that's done, hopefully, you know, a fixed number of times and repeated. And you can see that in some places, if you don't have a perfectly, you know, equidistributed surface area, there'll be a little communication imbalance. In other places, there's a computation imbalance if you don't have equidistributed interiors. But we have good graph algorithms with weighted nodes and weighted edges that can do an extremely good job equidistributing even a trillion point domain over 1 million processors. And it's really just a very simple loop, but nested and therefore sequential, and several synchronization points in this loop. Of course, the hard work in the inner loop is done concurrently. That's how it's a parallel computation. So with that kind of a machine in mind, that algorithm in mind, with regular synchronizations and regular near neighbor exchanges, what's the machine going to look like that we have to execute it on? I mean, it runs well today on a let's say 300,000 node IBM Blue Gene. There are many paths beyond CMOS and silicon, but not before we're supposed to cross that exascale line, right? And not in 7 years, 8 years. Probably one of the breakthroughs that we really need to look forward to is lower power, higher density memory that can overcome the memory wall. Maybe that will come from graphene or nanotube type devices. But and Jeff has done some work on that. But we're not there yet. I mean, not on the physics, but on the memory wall issue. Two paths from Peta to Exa seem forthcoming on looking at the industry, and they do come to these meetings. IBM is the only company that can do it all by itself. It already has 3 petascale architectures: the low power, high concurrency Blue Gene, the high power, low concurrency Power, as in Blue Waters, and the GPU type cell. And they've reached the petascale with all of these. Each one of these, the Blue Gene, the Power, and the Roadrunner at Los Alamos is a cell-based machine. Everybody else is going to just have to glue attached processors to their existing chips. That's how the Chinese got there, by attaching some NVIDIA Teslas to their Intel chips. At least for the PDE-based scientific codes, the outer loop will still look like message passing, but it will be message passing plus because of what's happening on the inside. This workshop that Jeff and I regularly go to has laid out a couple of what they call swim lanes of getting from today's petascale machine, like 2 petaflops, to the first exaflops machines. And I'd like to point out, that the increase, this should really say ratio, not difference. But there's 2 different models here, which, one of them says, let's go 1,000-fold on the concurrency per node and back off a little on the increase of nodes. And the other one says, let's go, as many nodes as we can and back off a little bit on the concurrency per node. But within that sort of factor of 10 slosh between what happens on a node and what happens between nodes, it's very clear that we're going to have 1,000 times more flops, but only 100 times more memory, and only 100 times more memory bandwidth. So the already starved memory and memory bandwidth conditions of petascale machines will get worse in a relative sense by an order of magnitude. And the worst part is this top number. We have to get 1,000-fold times performance in only 3 times more electrical power. That's an engineering challenge. The reason for that is 20 megawatts is the cost of powering up a small village of 14,000 people. You and I are each burning 1.4 kilowatts continuously if we live in an OECD country. And so that's 14,000 of us, or a machine. I mean, what would you choose? In terms of sustaining. Can't afford too many machines by displacing that many people from the Earth. So take the sort of a straight line scenario. If you extrapolate today's memory down to, let's say, the 30 picojoules per bit range, and it's a fairly cheap technology push to do that, then what do you get? You get about by 20 megawatts, if you assume the memory can use half of it, you get less than a tenth of a byte per flop. How many bytes per flop would you like? Well, suppose you're doing A plus B goes to C in double precision. That's 24 bytes of memory access. 2 words in, 1 word out for 1 flop. We're talking about 1/10, not 24. So we're almost, 1.5 order of magnitude down with the sort of extrapolation of memory as it is. If we go to more aggressive designs, what could we fit in for 20 megawatts? We have to really reduce the number of picojoules per bit to transfer a word. And of course, the memory is much more expensive that way, but maybe we can get up to a byte per flop. Maybe we can, but that's the best. That's the best scenario. This means you can hardly ever use memory. You can access your memory once, and then you better use it tens or hundreds or thousands of times close to the processor in registers, because that trip from CPU to memory is just way too expensive. People need that energy to fly and to harvest food and to do other things. We can't just be moving numbers around, right? Then there is the cost of buying all that memory. Under sort of some straight line extrapolations, maybe this is the $100 million memory price point line. On an exascale machine, you get less than 100 petabytes. Are you lucky? Do you get 100 petabytes? This violates the Amdahl case rule. Amdahl and Case said for every flop you should have a byte of storage. Well, we have to work with smaller workspaces. But the good news is flops are free, so we can recompute things instead of storing them. Why do we need so much concurrency? It's because of this nasty cubic law between power and frequency. Today you have a laptop with a gigahertz processor. It draws a watt. You want to get 4 gigahertz. You can have 4 1-watt systems, and it only costs you 4 watts. That's fair. You wouldn't expect to do better than that. If you try to crank up your frequency to 4 gigahertz on one processor, the cube power frequency law says that you're spending 16 times as much power to get that 4-fold reduction. So that's why the machines are going highly multi-core instead of faster. So these are some implications. Expanding the number of nodes, that is the processor memory units, up to 1 million is not a serious threat. By the way, I forgot to point out something. Yeah, did you see that title in italics? We're talking about a gigahertz kilocore mega node system. 10 to the 9th, 10 to the 6th, 10 to the 3, it multiplies out to 10 to the 18th. That's your exa, right? So the nodal concurrency is about 10 to the 6th. And MPI goes there today, almost. I mean, it goes well up to just below that, and it can probably go there. I mean, you need to allocate more space for buffers and stuff. But this is actually not a hard thing to do. The real hard thing to do is the 1,000-way parallelism within a node, which has to be strong scaling because you're not getting that much more memory. And the memory bandwidth will expand by, at best, a factor of 10 less than the number of flops that are supposed to be executed. It's already about 1,000 times slower to get an operand from DRAM into a floating point register than to do the operation. And this will get worse by about a factor of 10. So almost all operands have to come from registers or upper cache. This will mean incredible rewriting of methods. Probably we can't store sparse Jacobians anymore. You only use that element once in a MATVEC. So this is a draconian reduction that is required of users of these machines in power per flop and per byte that will make computing and copying data less reliable. The engineering solution to fitting this machine in under a 20 megawatt power limit will be really making the difference between a 0 and a 1 almost noise level in the semiconductor technology. The circuit elements will be smaller and will be subject to greater physical noise, like the power bus running next to it or the cosmic ray. We'll do all our computing deep under the earth instead of on the mesa at Los Alamos. There will be more errors that must be caught and corrected, and this will make the thing performance non-uniform. Power will have to be cycled on and off. We can build a machine with all these pieces, but we can't turn them all on at the same time. And so this makes the performance per node unreliable in another way. If you look at the sources of non-uniformity, we already have things like manufacturing and TLB CAS mishes and so forth, OS jitter, but we have new ones like dynamic power management, higher frequency of soft errors, higher frequency of component failures, the extra software needed to recover from the recoverable errors. And these kind of things will really make it hard to estimate how long one of these supposedly synchronized node tasks will take. We're used to dealing with non-uniformity today as clever programmers. We put in adaptive meshes, adaptive orders of magnitude of discretizations, adaptive physics, and we can control load balance because we know exactly how the hardware is supposed to be. It's hard, but we can handle these things. But now we got a whole bunch of other ones thrown at us that we can't predict. And they look the same when it comes to waiting at a synchronization point. So any solution for the top line will actually liberate us from all the hard work on the second line. The piece of MPI is over. MPI is not over. Okay, but the peace of MPI is over. The peace of MPI said that for a couple of decades, you had a universal language, which meant things were really portable. And you could compile, link, and run the first time from Gigascale to Petaflop, from Linux clusters with loose Ethernet connections to high-end systems. We protested, but it was really good. You'll miss it. It conferred advantages. Now, of course, MPI continues for a long time, but not MPI only. And it's that plus that will make your code non-portable. This reminds us of another nice pax that the world had. When the entire Mediterranean was governed by one ruler. And there were safe roads and uniform currencies, and you could trade freely, and you had predictable taxation, and there are no pirates. The occupation was protested, right? But it had some advantages. Well, Rome continues to exist for centuries, but it breaks up, right? It becomes much less universal. And that's where we're heading. So some themes: clock rates will cease to increase while arithmetic capacity increases dramatically through extra concurrency. Storage capacity diverges exponentially below the arithmetic capacity. It increases, but not as fast. Same thing for bandwidth. Mean time between hardware interrupts shortens. And billions of dollars of scientific software hang in the balance until you guys, who are under 30, come up with better methods, because it's your scientific future more than mine. And Moore's law does not end. We can still double the number of transistors per centimeter squared every 12 to 18 to 24 months, but the Dennard scaling, all those nice power features that go along with miniaturization, no longer work. And so the applications people in the Exascale program are moaning about all of these things. Memory bandwidth is already limiting, and now you're going to make it worse. But processors, because they're cheap, it makes sense to flood the nodes with them. If you can only use them once in a while, that's actually good engineering design. They're cheap. But it means that the denominator is spoiled in your efficiency estimates. You have this machine which is technically capable of an exascale, but realistically you could never move around data fast enough to use it all. So it will look bad on your efficiency plots. But that's okay. It's actually the right engineering decision to make. Now, one of the things, probably the worst news to the exascale community is the fact that one of the great hopes for the exascale, namely you can take many complex models and glue them together. You have an ocean model, atmosphere model, polar ice model, terrestrial gas exchange model, and they're all well-designed codes that work. And you say, okay, put one in this chunk of memory, put one in that chunk of memory. Because we can't pass that data, the fluxes and the forcing terms and the boundary conditions around. We can't afford to pass them around. We're actually going to have to rewrite those codes to put everything that belongs together in space together. There's going to be a lot of code rewriting. It won't be just loose coupling at the exascale, even though that's how it's being sold to the government. There are a number of issues here that I think, because of the way I've been using time, actually we started a little bit late, and I can maybe, should I try to make up time and pretty much end on time? I mean, okay, because people have other things. Okay, so let me just show a movie for the rest of the time. I think I've sort of stifled your enthusiasm about the exascale with some of the problems, but I'll show at least a few ideas about solutions. I mean, these are the four things that applications people are really worried about. Let's go to the bottom one. Let's go to programming model. We can prepare now. In fact, every high school kid in America is preparing, because they all have a PlayStation and they all have a laptop with 4 nodes, and they're all figuring out how to use shared memory programming with CUDA and other things. But one of the things that we need to do is worry about why we're moving so much data. Today we use double precision words like they're free. Take a movie of an element of your state vector, the pressure at a node in your fluids computation. After a few iterations, the leading many bits stay the same, and you're just getting a little more accuracy in a few bits at the end. But we pass around the whole bloody word. What we need to do is compute and store and pass the deltas. We need to do data compression on the fly. We need to have networks that can subtract out all the bits that are the same and pass the deltas and reproduce them on the other end. There's a lot of ways we need to rewrite stuff, because now the goal is reduce storage and motion. Flops are free, and flops can be used. We need to hybridize the concurrency scale, the coherency scale of data. MPI is nice because no one else can touch your memory. Shared memory is hard because everybody can touch it. And there's probably some hybrid that's best, and maybe even multiple levels where if you change one bit and it needs to be consistent, the number of neighboring memories that have to be updated on that snooping bus is relatively small. Hybrid programming does work. Here's a special model. Here's a full-fledged application. This is MPI only, and this is the running time still going down if you hybridize. But hybrid programming models are not enough. We need to actually rewrite algorithms in terms of work that's scheduled and ready to go when the arguments become available. If you think back to my PDE simulation, we have a linear solve, we bound the step, we update. We do a linear solve, we bound the step, we update. That's a non-negotiable inner loop. But we throw a lot of other stupid things on that inner loop. We recompute the Jacobian and we refactor the preconditioner. We test convergence, we adapt parameters, we do I/O, we do viz, we do data mining. Those things are not on the critical path. You can leave those as work to be stolen by the less busy processors if you can rewrite your main loop as sort of a directed acyclic graph. A lot of deterministic linear algebra, direct linear algebra has already been done this way, but we haven't yet gone into iterative methods and taken full advantage of that. So we have to create separate threads for logically separate tasks and throw them onto the system like an operating system throws tasks with different priorities, wake them up when their operands are ready, hopefully mostly their local operands. There are a few language stabs in this direction. We need a lot more. We need to go back and look at all the algorithms that were suboptimal because they were less synchronous. On a good machine, you wouldn't use these, but on a lousy machine, they're actually maybe competitive. The things you need to do to get to Exa are all going to do great things for your code today because we're already memory starved and memory bandwidth starved. So we might as well start working on the things that are going to get worse. It's not a risk. It's not an investment that will go away. We can use it now. So let's see. Mainly within a node, I said I would just show a movie, and that's what I'm doing. Three pathways. Weak scaling up to the number of nodes, strong scaling within a node, and scaling the workflow. Having a large number of cases that are moderately independent, that all belong together to the completed solution. Maybe a number of different wave numbers in some neutronics calculation. They replicate the spatial domain and do the wave numbers independently. There's a lot of that was a Gordon Bell Prize a few years ago. There's a lot of clever things to do. This is the software that has to be moved. This is the stuff that we use at the high level to discretize, solve, visualize, draw scientific inference. This is the stuff we need to develop the code, like even a simulator for the machine to know how the cache works and so forth, debuggers, profilers. This is the stuff we need to run the production and to get the data out. None of it comes with the machine, of course. This is what DOE labs are for, and this is what graduate students are for. And I have this little niche, but I hope you guys are working on the other bullets, because we all need to get there, and that's what this international coordination is about. So there are various, I could recommend to you various algorithmic research directions, but I really recommend mixed precision, because if we can reduce the number of bytes that we store and move to the ones that are actually moving, that's going to be a big win. Iterative correction is a classical idea from linear algebra. You do the n cubed work in single and the n squared work in double, and you just save tons. And some of what we need to do to overcome the machine non-uniformity will help us relax on some of the hard work we do with adaptivity. We don't want to concentrate on the efficiency because it's an elusive number. We want to concentrate on isolating at every stage what is the limiting hardware resource and restructuring that local phase of the code to make the best use of that resource. This is, I guess, just going quickly to the end. You can have these slides. In fact, they're probably on the web already at various places, and this is being videotaped, and the slides will be part of your archive. We reflected briefly on the good news, Gordon Bell and top 500. We peeked briefly at a motivating application and its Achilles heels of synchronization. We looked generically at this PDE simulation, and weak scaling is fine, but there are some specific hurdles posed by the high end, and this is my second last slide. And in 1962, a US president set forth a very difficult goal that was supposed to be accomplished within 7 years. We choose to do these things not because they are easy, but because they are hard, because that goal will serve to organize and measure the best of our energies and skills, because that challenge is one that we are willing to accept, one that we are unwilling to postpone, and one which we intend to win. And on July 20th, 1969, human beings walked on the moon. Will by the year 2020, will human beings be using exascale machines? I'm not sure. But we have a good petaops machine to get us there. This is a very low power machine. A few pounds of food per day. It doesn't generate a lot of heat. It doesn't do floating point operations, as we know. We can't even balance our checkbooks. But it does. It's a new formulation of the problem that's very efficient. I think it's a good paradigm for what we need. And let's talk about the Exascale next time. Thank you.
So David, thank you for the visionary talk. On behalf of the School of CSE, we have this distinguished vase for you.
It is indeed.
Engraved.
Thank you.
For this keynote talk.
Engraved for Hamming's birthday.
And a gift.
Thank you so much. This is a very moving moment because I actually feel sort of like an insider in your school from all the friends that I have here. And it's great to share. It's just a day. You've been doing this for 5 years, but now it's official. And thanks for letting me be a part of it, David.
Thank you.
And Richard. Thank you. Thanks.
So maybe there's time for one or two questions from the audience.
You showed that slide at the very end of the human brain.
Yeah.
With low power requirements.
Yeah.
Doing sort of interesting things.
Yeah.
Can you speculate on the possibility of sort of specialized analog hardware coming into play?
I mean, I put it up there to be provocative in hopes that somebody who knows a lot more about neuroscience will be able to do that. I mean, this is, of course, I always like to say the grand challenge of computer science is understanding the machine itself, not the simulations that we run on it. And this, is this is the ultimate grand challenge, to understand this machine. I don't know enough about physiology or, the way the mind responds to stimuli to guess how we would mimic that power in hardware. Of course, neural nets are a very rough way of doing data mining on patterns that can be represented in computer memory that may show the way. I mean, all the algorithms that we can think of, these kind of things, they're not optimal yet. But it's a very good question, and maybe just this juxtaposition of the very difficult task of doing it with CMOS and the existence proof that we can do certain other things in a complementary formulation better is going to help. Thanks.
Other questions, Richard?
Yeah, Richard.
I wanted to come back to the comments you made about the fourth paradigm
Yeah.
in connection with the exascale.
Yeah.
On one hand, one can look at the exascale, and you very articulate very well that this is really tough for simulation problems. If you apply that to data, a message could seem this is maybe hopeless. I was wondering if you had thoughts on that.
Yeah, certainly one of the things that simulations have going for them in a world which is bandwidth starved is we can actually, and you could also say latency limited because of this 1,000 flop cycle time to get a word in and out of memory. The good news is that in simulations, we can predict our data needs far in advance. We're going to run this loop 10, 100, 1,000 times. We know what parts of memory we're going to touch. We can get those flows going. We can figure out where to keep the most commonly used ones right in processor. With some of the more, some of the things that are much more data dependent in terms of how the operations are scheduled, including data mining, transactional databases, and so forth. I think we're going to lose that advantage that we have as engineers in designing a close to the metal code. So I'm less optimistic about using that efficiently. But remember, though, that it's the memory that's the expensive thing. So if you're already going to pay for an exabyte of memory and you're going to put valuable data in it, it's maybe okay not to be so efficient on the flops. I mean, you don't want to keep it powered up longer than you need it to be, but but you're really thinking about the machine in a different way. You're thinking about the machine as an expensive place to hold data, and hopefully you can get some, performance out of accessing the data, as opposed to thinking about a machine that does flops. So the perspective, I mean, it's still a harder problem, but maybe the, putting an exaflops metric on it is not a fair thing. So I think that the data frontier is, because it's much less explored, a much more promising one. Yeah.
A lot of these topics seem to require reevaluating a whole stack of professional standards down to even a
Like,
issue with mixed precision.
yeah,
Point,
yeah,
you have
I know.
small next point away.
Yeah, yeah.
So any ideas on what directions people should get started for those? Because even just revising standards.
Yeah, I actually, this is an interesting question. I was, just earlier this week, I was having lunch with the research VP of AMD and about 7 of his staff, and we were talking about both mixed precision, low precision and unreliable, for instance, if you're doing an error, if you're doing a computation, you have an error in a pixel and you're making a movie, that's okay. But if it's an error in your address to the next element in a list, it's not okay. So data that we have in our programs will have several dimensions worth of declarations. Can it be corrupted or can it not be? What is the actual optimal byte length, and does that change? How can it be replicated? What is the coherency domain of? These are definitely parameters that we don't have to think about in programming today. And as you say, it will probably be a big jungle for a long time, and maybe some sensible standards will emerge. It's certainly not going to be a safe place to go work. The only people who will do this are crazy scientists who really want to know the mass of the proton to the 20th place, or who really want to, make a good financial estimate of the cost of, putting carbon into the atmosphere or something. I mean, people who just want to make money or, stuff like that. They won't consider this an attractive enough environment. This will be the kind of thing that governments and strongly motivated pioneers go into for sort of narrow reasons at first. But just like the space race gave us Tang, the exascale race will give us better computers for the commodity market too.
So let's thank
Okay.
David again.